So we're going to start section 6.2 with a proof of the Pythagorean identities. We know that sine squared plus cos squared equals 1 just because of the unit circles, right? This is cos and this is sine and this is 1. So sine squared plus cos squared equals 1. Now, if you divide everything by sine squared, that means this part becomes 1, this part becomes cotan squared, and then 1 over sine squared becomes cosecant squared. So that means that 1 plus cotan squared is cosecant squared. That would be the proof of how we got this next identity. Let's look then at our other identity. If we divided everything by cos squared, sine divided by cos is tan, cos divided by cos is 1, and 1 over cos is secant. So again, just by dividing everything by cos squared, we can manipulate our first Pythagorean identity to get tan squared plus 1 equals secant squared. Alright, section 6.2 says the sum, difference, and double angle identities. So now we're going to do all the rest of the identities from your formula sheet. Now this is very important. A common misunderstanding by beginning students of identities is to think that cos 45 plus 25 is the same as separating it into cos 45 plus cos 25. But since 45 and 25 degrees is talking about angles around a circle, we have to treat this differently. So you can't just split something like this up because we're talking about where it is around a circle. So there is a way to find the expression though for cos 45 and cos 25 in terms of trig functions, and that's the focus of this section. So these are all the rest of our identities that we're going to be dealing with. It's very important that you understand how these work. So the sum and difference identities are because there is adding and subtracting. So the sum and difference means the adding and subtracting identities. Now if you look, these all follow a pattern. So sine of x plus y is equal to sine x cos y plus cos x sine y. So x here is talking about one angle and y is talking about another angle. So you have to be very particular about making sure that the sine x is first and the cos y is second and so on. So you have to follow the patterns closely. The double angle identities mean that the angle is double what it was, what the nice angle was originally. So for example, if x was 30, then we'd be talking about a 60-degree angle, because 2 times 30 is 60. Again, it just follows a pattern. The only one here that's tricky is cosine, because the double angle identity for cosine actually has 3 different options. So when you have a cosine double angle, you're going to have to pick which one you think would work best for the situation you're given. Alright, so here let's try our first example. The sum and difference angle identities can be used to simplify more complicated expressions that follow the correct pattern. That part is so important. You have to make sure the pattern is correct. So let's look at this one. Sine 140 cos 50 minus cos 140 sine 50. So this one goes sine cos minus cos sine. So let's look at our options here. We're looking for one that goes sine cos minus cos sine, and it's this one. So that means I can simplify it into sine of x minus y. So when I go here, I'm going to say that this is sine x minus y. Now the x was the first thing and the y was the second thing. So this would be sine of 140 minus 50 degrees, which simplifies to 90 degrees. So this here would just give us sine of 90 degrees when we simplify it. Alright, so our next one we can change into cos x plus y. Again, here the x is 36, the y is 24. So that's going to be 36 plus 24, which is 60 degrees. Notice how the angles that I'm getting are nice angles. So if you were asked, you could look up these values on your unit circle. Right? You could look on your circle and find sine 90, or you could look on your circle and find cos 60. So they're meant to give us nice values. Let's try C. Tan 17 minus, that's plus tan 13, and then 1 minus tan 17, tan 13. Right, so that's tan x plus y. So go back to this question. Tan x plus y, which gives us, if x is 17 and y is 13, this is 17 plus 13, which is tan 30. Good. So now we're going to look at D. This one is going to trade into sine 2x. So my x is going to be 22.5 degrees. So we're going to go sine of 2x. And again, it's 2 times 22.5 degrees. So when you multiply those, you should get a nice 45-degree angle. Again, notice that all of my angles have been nice so far. Next one, E. Cos squared of 15 degrees minus sine squared of 15. Cos squared minus sine squared is the cos double angle identity. So cos of 2x. And this time we're going to put in 15 degrees for x. So we get cos of 30 degrees. All right, so for these questions, we're trying to get it to a single trig function. So we're going to start with A by looking what we can trade. So sine 2x. I know that sine 2x is the same thing as 2 sine x cos x. So I'm going to trade the denominator for 2 sine x cos x. Now the top has a cos 2x. But what's tricky with cos is that there's 3 options for the double angle. So you have to pick the option that will hopefully give you something that will cancel with your denominator. So we're going to try this one because of the 1 in front. So 1 minus 2 sine squared x. Now when we put the negative in, we're going to get 1 subtract 1 plus 2 sine squared x over top of 2 sine x cos x. And we're just going to continue simplifying. So 1 subtract 1 is 0, so that's going to be canceled out. So then I'm left with 2 sine squared over 2 sine x cos x. Is there anything else that we can divide out here? The 2's and one of the sine x's. Good. So that'll leave me with a sine x still on top and a cos x on the bottom. Why is there still a sine x on the top? It was squared, right. It was squared, so there was 2 of them at the top. So again, one of them is going to get divided out, which leaves me with tan. So tan is the simplified answer for this question. So for part B, we're going to trade the cos 2x with 2 cos squared x minus 1, because then my minus 1 and my plus 1 will even each other out. After that, we can just divide out our 2's and one of our cosines, so that we're left with a simplified answer of just cosine x. So for these next questions, we're going to be finding exact values. Exact values, if you'll notice that here we have a 75-degree angle. 75 degrees is not one of the exact values on our unit circle, but we do have 2 nice angles on our first quadrant that we could add together to get 75. So I'm going to rewrite this as sine 30 plus 45 degrees, because 30 plus 45 is 75 degrees. So I haven't changed the question, I'm just rewriting it. Now when I look at my identity sheet, I see that sine x plus y can be rewritten as sine x cos y plus cos x sine y. So I'm going to expand this by writing sine 30 cos 45 plus sine 45 cos 30. So just following the pattern from the identity. So our next step then is we're actually going to trade these with their exact values. So sine at 30 degrees is root 3 over 2. So I'm going to trade sine 30 for root 3 over 2. Cos 45, oh sorry, I said that wrong. Thank you. Sine is the second one. So actually sine 30 should be 1 over 2. Sorry about that. That's sine. Cos 45 is root 2 over 2. Sine 45 is also root 2 over 2. And then cos 30 is root 3 over 2. So those are all of our exact values. Now we can simplify them. So we've got fractions that I'm multiplying. So we go top times top, bottom times bottom. So we end up getting root 2 over 4. This side, we have root 2 times root 3 is root 6 over 4. So my final answer would be root 2 plus root 6 all over 4. Now you can't add root 2 and root 6 together because they're not like roots. They're not the same root, so you can't add them together. So that would just be your final answer for sine 75 degrees. All right, so for cos pi over 12, just think about this. It might be easier to think about this as 15 degrees, because pi over 12 is half of pi over 6, which means it's half of 30 degrees. So we're saying that it's a 15-degree angle. So really what I'm doing then is I'm taking cos, and I need two things that give me 15 degrees. So we might say 45 subtract 30 to get my 15-degree angle. So now if I look at the equation for cosine, so take a look at the rest of part B, and you should get root 6 plus root 2 over 4. All right, so 105 is 1060 plus 45, and then we can plug that into our formula. But now, to find the exact values, we have to look at our circle. So here is 60 degrees right here. Remember that tan is sine divided by cos. So the denominators will cancel. So we're just left with tan is root 3 over 1 for that part. We're going to put in a root 3. Tan 45, when I take my root 2 divided by root 2, we just get 1. So root 3 plus 1. And then on the bottom, I'm going to use those same two values, because tan 60 again is root 3, and tan 45 is 1, and I'm multiplying. So what that gives me is root 3 plus 1 over 1 minus root 3. So remember that since you can't have a root on the bottom, we're going to have to multiply everything here by the conjugate, and the conjugate is the same thing but with the opposite sign. So this was all from Pre-Calc 20, where you multiply things by the conjugate. Now, when you multiply this, it's just a FOIL process. So for the top, it's going to be root 3 times 1, which is root 3, root 3 times root 3, which is root 9, so just 3. 1 times 1 is 1, and then 1 times root 3 is another root 3. In the bottom, it's going to be like a difference of squares, which is why the conjugate helps us. So 1 times 1 is 1. 1 times root 3 is plus root 3, but then minus 3 times 1 is minus root 3, and then minus root 3 times positive root 3 is going to give us a negative root 9, which is a negative 3. So what you should notice is that your plus and your minus root 3's will eliminate, just leaving you with a denominator of 1 subtract 3, which is minus 2. But on the top, I can combine like terms, so 3 plus 1 is 4, and then 1 root 3 plus another 1 root 3 is 2 root 3's.
Can you just put root 6?
So to get our final answer, I see all of my leading coefficients are divisible by 2, so we'll divide them all by 2 to get our final answer. So for our last example today, we were given some information to create two different triangles. So we've called them triangle A and triangle B based on the angles given here. So angle A, angle B. So now let's start by finding sine A plus B. So the formula for sine A plus B is sine A, and I'm just going to use regular A and B, but it's sine A cos B plus cos A sine B. So where we go with this then is we look on our triangles, and we're going to start by finding sine of angle A. So I look on triangle A, sine is opposite over hypotenuse, so sine is going to be negative 3 over 5. Again, we're just keeping our values exact. Cos is B. So now I'm going to look at triangle B, and I'm finding cosine. Cosine is adjacent over hypotenuse, so that's going to be 2 over 3. Now we're going to go to cos A. So A, again, back to triangle A, cosine is adjacent over hypotenuse, so negative 4 over 5. Then we're going to sine B, back to triangle B. Sine is opposite over hypotenuse, so that's negative root 5 over 3. So that one then we just finished off by multiplying our fractions and simplifying. For part B, we're finding cos of the double angle. You could pick any of the double angle identities. I just chose this one. So let's find cos of B. Cos of B is 2 over 3. So I'm going to trade cos B for 2 over 3, and then I'll still have to square it. Sine at B is opposite over hypotenuse, so that's minus root 5 over 3, and again we're going to have to square it. So we'll just come up with an answer of minus 1 over 9 when we simplify. So you can then try these questions and have them ready for tomorrow.